Okay, so you can see my screen? I guess so. Great. So, yeah, my topic is about static semantics of rank polymorphism. So, the subtitle could also be about running APL on GPUs using Idris. So, the first thing I could cover is the definition of the title. So, what does actually static semantics mean? Well, it's about abstract interpretation of something. So, it's about this information that we can know about programs before we start them. And this has been researched quite extensively by a lot of logicians. And one of them was Kurt Gödel, who made this incompleteness theorem. So the kind of like the point we can take from that in this study is that it's very hard to interpret programs, even if they're simple. And then the other part is this rank polymorphism. So rank polymorphism adds this value-based context to the language interpretation. And for example, Finnish, which is my native language, has a certain kind of rank polymorphism as a semantically same things, the kuusipala, means different things depending on the context. So in Finnish, you cannot really know what someone is telling you unless you know the bigger context of it. Or it might be that you can interpret what they are saying, but your assumption can be wrong. So then kind of like combining these two properties together is then the kind of like the topic of the thesis. So how can we know something about program beforehand, but at the same time have it semantically look the same, but do different things depending on the context or the parameters as it is kind of like translates to. And then what is the reason I'm studying this is then regarding parallel programming, which is considered usually a hard thing to do, but it's kind of modern. So about these multi-core systems and GPUs and TPUs and so forth. So the main point of parallel programming, or one kind of like notion of it, is that accumulators are very bad. So accumulators would be like how you would usually do maybe a loop. You first define a variable, and then you go through a, let's say, list of numbers, and you kind of like count the number or the elements of the list by always adding a single value to the accumulator or the variable you defined first. And then in the end, the accumulator will tell you the result. And then divide and conquer takes a different approach. It takes the initial list and it splits it up into smaller pieces. So the computation graph kind of like it expands and then it reduces. And the reduction is then your final result. So we will have some examples on that later. But anyway, the problem with this divide and conquer is that even though it's very fast on a multi-core system, it's kind of like hard execution strategy when we do not know about the troops or the resources that we have available. So on the right hand side you can see this table about GPUs and some of these physical properties that they have. You don't really have to understand what is a subgroup size or queue family or queue length, but the point is that depending on the hardware, the physical properties of the GPU change, and this can create this very kind of weird combination problem, I guess. And one of the maybe like more apparent problems of this is that, for example, the Apple M1 chip has it's marketed as an 8-core GPU, but what the graphics API gives you is 4. So it can be that the programmer doesn't even know, or he's been told, or they have been told something else about the hardware they have. So the problem is that we would need this kind of dynamic scheduling then to kind of like abstract away these things which programmers shouldn't probably think about or worry about anyway. And the interesting remark here is then these array programming languages, they abstract away this execution strategy. So APL is one of those. So on the left-hand side, you can see a matrix definition, 3 by 3 matrix, and then you decrement a single value from that, each of the values of the matrix. But the point of APL is that it doesn't tell you whether you use or whether it's using an accumulator or divide and conquer strategy. And that's kind of like the interesting thing. So, and then on the other hand, it also has the notion of rank polymorphism. So on the middle, you can see a vector being defined, a four value vector, and then you do a sum reduction on it, and you get 10. But again, APL does not tell you whether it takes pairs of values, like here it would take 1 and 2, and then 3 and 4, and then sum those values, and then sum the result of it, or whether it goes one by one of each value. And that's kind of like interesting part of it. And on the other hand, on the right side, you can see that the sum reduction and the kind of like the decrementation of values also works depending on the context. So the context is now brought here in the form of a parameter rank. So the sum reduction works whether you have a vector or a matrix. But the point is that APL is kind of like interesting on language or a family of languages to apply this kind of like static execution strategies, because array programmers do not care or do not know how they actually compute the values. So then the motivation of this study then becomes about this information on how many troops we have for our divide and conquer strategies. So there's some practical reasons to do this. First is typing for GPUs. So once you have strong typing, it kind of like facilitates these divide and conquer strategies. It facilitates the splitting of the work. So it allows you to gain the whole efficiency of the hardware you have. And another thing is that, on the other hand, it would be very nice if a single program would work on any GPU. So it would be kind of like awkward if you would have to make changes to your program depending on what kind of hardware you have. So for programmer, it would be first about, oh, what kind of computer do I have, and then about programming. But that hardware part should be abstracted away, I think. But then there's also these theoretical parts. The first one is advanced type systems. So the way you kind of like can achieve this is with advanced type systems. And it comes down to this question about what can we know about programs before we start them. And then on the other hand, there's also this array programming properties. So then of the information that we know about the program, how can we generalize it and adapt it depending on the parameters? So the way I was doing this in this thesis was then Idris. And Idris could be considered for us approach to do abstract interpretation on types or so forth. So Idris is a Haskell-inspired language developed at St. Andrews, and it's about like dependent types in the sense that types are determined by values which create universes. And I have an example. That's one take you can have on it. And that the types here are more abstract, or it's more like categorical theoretical sense. So it's more about what are the categories of arrays rather than just whether I have an integer or float. And Idris also allows us to form theorems about programs which then require recursion-based proofs. So on the right-hand side on the top, you can see this example that, for example, a 0 in Idris is z, and 1 is the successor of 0. And 2 is the successor of 0. So there's some of these notions that these logicians found out in the last century was that you cannot really know much about programs unless you base it on this well-defined recursion. And then kind of like another take how we then actually do the abstract interpretation with Idris is that, for example, we have this opinion. We say that any array is a matrix. So on the bottom you have this other image, and there it says that you have a shape, and shape is something that takes first a parameter of rank, and then it takes a second parameter of dimension, which then has 3 different parameters. And that's not kind of like the important part, but the important part is that we can say that we have some scalar or some vector or some matrix. We can make the system in which we abstract away. We don't care about the values we have on some vector, for example. We are just interested in the type of it. And we can do also this kind of like fancy thing in which we can say that, well, the matrix is the most general version of some array, and then a vector is a special case of matrix which just has a single row, and some scalar is just a special case of matrix with a single row and a single value. But this kind of like notion that we don't care about the values is very essential in this work. So the another thing is this parametric polymorphism that you can achieve with Idris, and it comes down to the notion of universes or so forth. So maybe this is kind of like too mathematical or maybe not that practically interesting, but the idea is that we can have a function called reduce, which takes a shape and it outputs a face. But the point is that this reduce function doesn't really exist unless you have the shape first. And once you have the shape, the version which you apply is dependent on the value of the type. So if the rank of the shape is a scalar, you apply the topmost version of it, so on the line 57. And if you have vector, you then apply the one on, or the interpretation on the line 58. And then if you have matrix, you apply the bottom one. So in this sense, it shows that the applied variant of reduce is dependent on the shape's rank, so the first parameter, and this is kind of like how you can then achieve the rank polymorphism thing. So then, how do we type APL with Idris? Well, in APL you could have some program on the left, like adding a vector or adding a matrix to a vector, and APL might give you a type error, and it will tell you something about it. But the problem is that if this vector or the matrix would be huge, it would do the computation on those, and then you would only finally get an error saying that, well, we kind of like lost it, you had a problem way down the line. But in Idris, we can, if we abstract away now the value, so we just say that we have some vector and we have some matrix with some dimension, we can know before the value-based execution that there will be a type error, and Idris will be very verbose about it, but it will say that there's something wrong in it. And then on the other hand, if the typing is correct, APL will give us a value, but on the other hand, Idris will just tell us that, well, the result will be some scalar, but Idris does not know what, but it will kind of like give you this proof in some sense that there will be some scalar in the end. So the conclusions from typing is that we achieved shape analysis with this approach. So dynamic languages like APL could be enhanced with dependent types, and even without semantic changes to APL, which then kind of like give us confidence in the correctness of our programs. And then another interesting thing that the shape analysis gives us, or the abstract interpretation, is that we could produce SMT problems from Idris code. So once we kind of like only focus on how we can compute something instead of what we compute, the kind of like execution becomes a lot more abstract. So kind of like these divide and conquer strategies could be modeled as a statically optimizable problem, which thanks to the correctness assumptions and so forth is also satisfiable, and this would work within a GPU. So if you now have a computer and you have a GPU and the GPU has some physical properties, you could know that you can always split your work in an optimal way, given being the kind of like the physical properties or the kind of like the limitations, and on the other hand the features that your GPU allows. And then also interestingly within a node, so maybe now you have more GPUs, or within a network of GPUs. So once you kind of like take this abstract part, you could then kind of like think about your model, like what are the constraints of all the hardware you have, and why not only limit to GPUs, you could have TPUs and CPUs as well. So this is like kind of like the general direction, or this was something that maybe was found that maybe you could actually just model this as a kind of like optimization problems. So the takeaway comes down that parallel programming requires divide and conquer strategies. And these strategies can be inferred with abstract interpretation once we kind of like focus on how we can compute something instead of what we compute. And then the shape analysis is abstract interpretation of array programming languages, and this shape analysis can be captured with dependent types and languages like Idris. So in this work, we designed and captured shape analysis of APL using Idris. And in future work, it would be nice to then go on and automate the execution optimization of array programs. Thanks. Uh, yeah. Yes, that could be said to kind of like make it efficient to do computations on a GPU. Yeah. Yeah, well, the thing is that GPUs just tell you that, well, I have many cores, and it's up to you how you use them. So you can make a program which is slower than a CPU with GPU. It's very trivial. I've done it. So it's about like having a GPU just does not make your computation faster. It's also about knowing that how you program the GPU, which can be then hard unless you kind of like know or can make assumptions about the programs. Exactly. And that's also a good thing to note that uh, if you know about subgroup sizes and queue families and queue lengths, it's about the pipeline is this part. So how do you use the pipelines in an optimal way? So if you now have your array, how do you divide it between your queue families and which queues you use and so forth? So yeah, this is very relevant part of the work here. Yeah, I mean, most of the programming languages that you kind of like accelerate are already array based, but I would see that there's also this notion that what about if you now have different kind of hardware? Like it seems like the trend is going that you have GPUs and you have CPUs and now you have TPUs. So it's even though this thesis was more about GPUs, but it's also I think there's like a also a phase in which you could maybe try to abstract it I don't think it's scalable for a person to know what kind of hardware they have. So I think some kind of like compiler or something is required. So I think, but then the other thing is that I looked at the other of the uh, kind of like approaches or libraries which then distribute your computation, but the distribution strategies on those programming languages were usually dynamic. So it's kind of like the distribution happens on the fly, but there does not seem to be so much work on thinking about the distribution before the execution of the problem. So in that case, if you then, it would be more interesting, I guess, that you could then apply some kind of like constraints you want to your execution as you want. So yeah, I actually have let's say, I don't really note it in this presentation, but these actually the computations, they always kind of like return this phase, and this phase has the last argument is this something called, I call it mk par. So my point was that even though I did not extend it in this part, was that this mk par would carry over the dependencies. So it would kind of like describe to you whether the computation is like x wise or y wise. So it would kind of like, you could know that when some computation then requires the information from the different dimension, and that of course then kind of like affects how you are going to distribute your computation. But yeah, I kind of like considered that and how I could model it, but I did not. It's very kind of like tricky question, but in the end it seemed like APL could be reduced to a point in which you know that this is the smallest part of the, or this is like, this computation is now dependent on something, or like dependent on some values, and that you cannot kind of like split it into smaller pieces anymore. But yeah, that's also kind of like future work in some sense. Yeah, and I think it's already there. It's just in the form of NumPy and these other array programming libraries. I don't think APL is a language someone would end up writing. It's more about the, it's more for the people who write the libraries. So they write their libraries, maybe they use APL to model it, and then they give out this nice thing that they give, let's say, some random forest implementation or this machine learning application. But the programmer who uses that library does not know, they don't have to know that they are using APL, and that's not the point. So yeah. Yeah, I feel like the kind of like I would want to use some kind of proofs, or kind of like require some kind of like this implicit or kind of like explicit proofs on it. But and I felt like at some point it is kind of like, it fell short in the things I would have wanted to kind of like represent it, but the type system did not really work there. So at times I felt like I would have wanted to maybe use something like a ACTA or something, which is even more mathematical. And for a lot of work, Idris kind of like, it was nice and I got what I wanted out of it, but I think it might be challenging to try to extend it a lot. Great, thanks.